Hi, my name is Michael Hansen, and welcome to a video about observations and sensors. So, first of all, I would like to tell those of you who have watched some of my videos, or perhaps all of them, that I have not turned away from doing videos explaining things on my whiteboard, but it's simply a matter that I'm trying to use my iPhone as a camera because it can record longer sessions. It can autofocus, which my DSLR unfortunately cannot. It has some other advantages, but in this sense, the phone seems to be better. But I need something. I'm going to build sort of a little holder to put the phone in so I can have it on my tripod. Furthermore, for this presentation, what I'm going to talk about here, um, a slideshow like this just seems like a better solution. Alright, so one of the things that I've noticed is that for some flat earthers, basically, um, the argument seems to go on about doing observations and using our senses and all those sort of things. And I'm going to try to go a little into what our sensors, what our eyes, what our senses really are. I'm not going to talk about our hearing or our smelling or only our eyes, but I'm going to go a bit into that. And then move on to how we actually perform observations in for example, astronomy, and yeah, take it from there. One thing that really annoys me is when mostly flat earthers, of course, say that basically we shouldn't use aids, that we should use our senses, our pure senses, to observe. That really annoys me. And the reason is that what do these people think that we do with the observations we get from, say, the Very Large Telescope or the Hubble Space Telescope or ALMA or whatever the hell kind of telescope you're going to name? What do you think we use with those data? Do you think we just put it into a computer, let it crunch it, and then stick it in a paper and send it away without ever looking at it? Of course, we also use our senses. When we get an image from the Hubble Space Telescope, especially in my field where we are going to try to identify multiple images, gravitational lensed images around clusters or galaxies, we put those images onto a big screen, big fucking screen. And then we try to pinpoint with our senses, with our freaking eyes, where those images are. So there's no way in hell you're going to find any kind of scientist, student of science, or whatever in that direction you want, that doesn't use their senses. Now with this rant out of the way, let's get on to the subject at hand. Alright. I do apologize for the profanities. Alright, let's go on. As you can see here, Michael Hansen, it's me, June 11th, 2017, that's the date today. I've just updated this. For those of you who are interested, I have simply created this little presentation using the Beamer script or macro in LaTeX. Alright, so let's first look at the eye, what that actually is. So here you see an image of the eye. It actually shows how we produce an image in the eye. So what goes on? Well, actually we have a candlelight here, which are going to radiate light, as you can see by those lines here. And then we have the initial lens here, as you can see here, the iris. No, sorry, not the iris. The cornea, it seems to be, with a lens, an initial lens, that bends the light inwards, as you can see here. And then we have the actual lens here, which sort of focuses the light on the retina. And here we have the fovea, the point of central focus, and the optical nerve, and we also have a blind spot where you can actually test that. It's actually quite funny. But one thing you should notice is that when the light from the candle gets focused by the lens, it's upside down. Oh, darn it. That means probably that we shouldn't trust our senses, because if everything is upside down, I sure as hell don't see things upside down. I'm pretty sure when I look at this stapler here, it's pretty much upright the right way, so it's not upside down unless I turn it. So, but my eyes see things upside down. How can that be? In order to answer that question, that particular question, we would have to look at another crucial point in our seeing the world with our eyes. But first of all, I would like to point out just the basic things here. We have light from an object that gets focused by some kind of lens to an image on a detector. In this case, it's the retina. It is comprised of little cells that can see both colored light and black and white light, or gray nuances, if you will. I think it's the rods that can see color, and the staves that can see black and white or gray nuances. It can be that it's the other way around, but in any case, this is one thing that you can also test for yourself, just freely in your own home. The rods that can see, that only sees gray nuances, are much more sensitive than the staves. So what you might notice is that if you go into a pitch dark room, you of course can't see anything, but if you then turn on a little bit of light, then you can see things, but they are in gray nuances. If you turn on the light a little bit more, you might be able to comprise some colors. And then if you turn on the light fully, you'll see all the colors. That is because at first you're only using the rods to see whatever small amount of light gets focused by your eye. And then as you turn on the light, if you increase the light, the emission of your from your light, you'll see more colors, because then there's enough light to activate the staves also. Now I'd like to point out again, I'm not sure that it is the staves and the rods that do the things I say, but that is not crucial for the point either. Alright, let's move on, because what we have to introduce next is the brain. Because we have the eye here seeing some things that gets registered on the retina back here, sent through the optical nerve here, all the way up to the visual cortex, where actually the images are reversed. Because when we are born, it doesn't take our brain very long to figure out that, if you can say it like that, our brain long to figure out that the world is actually not upside down. So the brain somehow figures out by itself to turn the images in the right way, to interpret the images in the right way. But please be aware, be very aware, that whatever comes in through your eyes here gets interpreted in the brain before we actually register what is being seen. One particular example I would like to bring in is that our eyes are actually that sensitive to light that we could see a candlelight 1 kilometer or more away. Our ears, for example, is also so sensitive that we would be able to hear the molecules in the air hitting the drum. It is only because our brain has taught itself to exclude all of those things all the way from when the senses were active in the womb, not to overwhelm the brain and make us completely crazy. I'm pretty sure you can imagine if you could hear something like all the time in your ears, then you would go bananas. So, and also if you constantly had so sensitive eyes that you could see a candlelight a mile away, you would scream in agony just by turning on a little candlelight in your own home. So, just to point out that what goes in through our eyes is in very high degree interpreted by our brain before we register it actively. You can say that it's interpreted in some ways unconsciously. Alright, just a second. Alright, so let's move on to what happens in now let's go to and one thing that also annoys me a little bit is I'm pretty sure that any flat earther out there would say that I'm being silly if I said that they argued that being not able to use visual aids means that someone like me that has a, well, in lack of a better word, a construction error on my eye, I have to use glasses in order to. I can see without my glasses, but not as good. So I have to use the glasses in order to actually see small details. I'm pretty sure that any flat earther out there would say, well, of course you can use your glasses, don't be silly. Alright, I'm glad. But also something very simple like binoculars. I'm pretty sure that flat earthers wouldn't say that those are in any kind of conspiracy or anything like that. Even though you do have lenses and you probably have some kind of what's it called? You probably have some kind of prism in here, not a prism, but prism in here in order to move the light sort of in a triangular shape all the way out here. And you also have lenses here, by the way. So these are visual aids that can enlarge, and because you can imagine that our eyes are somewhat like I think something like perhaps a centimeter or something like that over here. So we have sort of an aperture of 1 centimeter. Here we have probably an aperture of 5, maybe 7 centimeters, something like that. So you can imagine that there's a lot more light being let in through these big holes here than our eyes itself, and then it gets focused out here so that our small apertures can actually utilize all the light that is collected. Alright, so these are visual aids that you can use every day in your everyday life when you go out watching birds or whatever you do. Try to observe the curvature of the earth, whatever piques your mind. Alright, let's look at the telescope and the CCD, which is the primary toolbox for astronomers, which for some reason flat earthers seem to think has some kind of conspiracy going on. But anyways, let's go on to that. So here is the basic setup. We have a big motherfucker telescope here. This is the Meet Max mount. I think its maximum capacity is over 100 kilograms, which means that I could form a neat little seat here, a seat that I could sit on, and then the telescope could carry me around. That would actually be pretty cool. But anyways, you have the telescope here. Look at this. This is probably something like 20-25 centimeters across, maybe 30 centimeters across. So you have a big opening here that can collect a lot of light. So I'm going to show you the diagram for a Newton telescope later on, but just to clarify in pretty simple terms, the light goes in, gets reflected on the primary mirror here, gets reflected by the secondary mirror here and out on the back of the telescope. And here where you have the focusing mechanism where the light goes out, you put on a camera. This is a CCD. I'm going to go into a little more detail about how CCDs and also CMOS chips works. But in any case, this is our lens, like we saw in the eye. This is the sensor, like the retina. And then you connect a computer. This is the laptop. I'm not doing commercials for Hewlett-Packard. Actually, I hate Hewlett-Packard. I have a Lenovo computer now, the former IBM ThinkPad. But I had a bunch of HP laptops, and they are pretty fucking nasty. I don't like them. Sorry. Sorry about that, HP. And so this is our lens, this is our sensor, and this is our interpreter. So in essence, if you want to convert this to the brain, this is the lens this is the lens in the eye, this is the retina, and this is the brain. All right, let's go on. So this is the basic setup of a Newton telescope. Now you can see here that for I think this is called a Cassegrain design. Perhaps it's a Smith. I'm not sure. I think it's a Cassegrain. But in here you have a hyperbolic primary mirror, as I think it is, and then you have also an inverted, not a concave. I think it's perhaps a concave secondary mirror that sends the light out of the back of the telescope. Whereas in the Newton telescope, you have light rays going into the front here, from the front, gets reflected on a, I actually think this is also a hyperbolic mirror, but in most Newton's telescope, it is actually a parabolic primary mirror. But in any case, light goes in, get reflected by the primary mirror. As you can see, it also gets focused, and then it is reflected outwards to the eyepiece or camera, whatever you have out here, through this slanted secondary mirror. Now, if this were a Cassegrain design, you would have a drilled hole in the middle of the primary mirror here, and then this secondary mirror here would be concave, I think it is, and would set the light rays back out this way here. Alright, so this is the primary design of a telescope. This is a reflector. If you had a refractor, the design would be pretty much like the binoculars that you saw, just with a bigger aperture and perhaps more lensing elements in order to alleviate some what's it called, chromatic aberrations and those sort of things. Alright. This is my telescope, so this is, as you probably can imagine and see, this is a Newton. I can go over what I have, because this is pretty important. Here you see, perhaps you can see, this is the spider web for, and the socket for the secondary mirror, which is somewhere in here around someplace. Then you have the primary mirror down here, the parabolic primary mirror. Here you have my Astro Camera, Starlight Express, and this is a filler wheel, and then you have the focusing mechanism here. This is the mount. For those of you who are interested in it, it's an EQ6 Pro, I think it's called, which is computer controlled. It can be guided and have go-to and all that jazz. What you might notice is that it has a peculiar orientation. Most telescope you see is called altitude azimuth telescopes, which basically means that they move sideways and then up and down. But this telescope here moves in a little stranger fashion, because when you set up the telescope, you have to point this area here, this part here, directly at the celestial North Pole. Now, one thing that could perhaps, I think, interest some flat earthers is that when I have a small pole scope in here, you can remove this cap here, and then there's a cap on the other side that you can remove, and inside that telescope is a pole scope. So it's something that is aligned, that when you turn the telescope around itself on this rect ascension axis, as it's called. So this big axis here is called the rect ascension, and this smaller axis here is called the declination axis. Just to point that out. So the rect ascension axis is always pointing towards the celestial North Pole, and I used the North Star Polaris to figure out where the celestial North Pole is, but you have to know the time in order to do that, because when you look inside this pole scope here, you would see a circle, big circle, with a smaller circle on and a cross in the middle. So the little circle should have the pole Polaris inside it, and the cross will then define where the celestial North Pole is. The interesting thing here is that you have to align this circle here by moving the rect ascension axis according to the time of day. So it would seem that Polaris is moving in a circular fashion with an period of 24 hours. That's actually pretty interesting. I'm not sure why that would be on a flat Earth, but nevertheless, let's go on. I'm not here to debunk flat Earth yet. Alright, so let's move on. So this is my telescope. I can take images with this camera here. These are not going through NASA or anything like that. They're going from this camera here, which I will show in a little bit, out through this cable to my laptop somewhere. Alright, here you have the guide telescope. Again, for those of you who are interested, this guide scope here will keep an eye on some star and then make sure that the telescope, the mount, is actually tracking the sky in the correct fashion. The advantage of this German equatorial mount, as it's called, is that when you have found something you would like to observe, you pretty much only have to move the rect ascension axis, because it follows the motion of the stars around. Alright, let's move on. This is the primary design of most professional telescopes. Again, you can see the same basic design as I showed you before. You have light going in, hitting the primary mirror down here, up to the secondary mirror here, and out through the back. As you can see here, this is an image I have taken from a trip to the Nordic Optical Telescope. You can see this is the back side of this 2.5 meter telescope. This is the opening that you can see that the telescope, it's daytime, so of course this is not opened, but this is where you point the telescope out. And this big chunk of different thingies back here is the different instruments. I think somewhere around here, I think it is, you have the instrument that we primarily used, which is called Alphosk, but they also have a fiber FET spectrometer called FIS or FIS, and then you can see there's some counterweights and different things around here. This is a professional telescope, unlike, for example, my telescope, which has a block mirror down here. So you basically take a big block of glass, and then you make it parabolic in shape. Then you coat it with some nice aluminium and something else, and then you put it in here. It's actually pretty heavy. With mirrors this size, if you try to do the same trick, you would get the primary mirror to bend under its own weight. So what's done instead is that you use some kind of aluminium or other kind of high reflective metal material, and then you put a lot of pistons underneath it, and then you use the pistons to shape the mirror in the correct fashion. The advantage of this is basically that you can keep an eye on a star, and then you can actually make the telescope bend the mirror in order to try to circumvent some of the seeing that you will see. Alright, let's move on. This is the primary design of the Hubble Space Telescope. Again, you can see, yeah, it was not concave, it's convex. Sorry about that. Again, you can see the same thing. Parallel light gets in, gets bent on this. This is not 2 blocks of mirror. This is a spherical mirror, sorry, a circular mirror, but it's seen from the side. You can see it here, and you can see light goes in, gets bent, and then back out to where you have the instruments back here. And these are actually pretty big. You might have heard that the Hubble Space Telescope is roughly the size of a big bus. But again, you have a concave mirror, and then you have a convex secondary mirror. For a Newton telescope, which I showed you before, the secondary mirror is just flat, but it's slanted. Alright, let's move on. The CCD. So this is a CDD with a Bayer matrix in front. Besides that, the cameras that you are using in your phones, in your DSLRs, pretty much probably are CMOS chips and not CCDs. There are some basic differences. The primary difference is, as you can see here, that all the pixels are not read out from a CCD at a time, but are instead read out like sort of a conveyor belt. So you read out this part here, move all the charges down, read out this part here, and then you continue until you read out all the pixels, read out all the pixels. In the CMOS chips, you have circuits for all the pixels, the individual pixels, so you read out the entire chip at one time. The advantage is that you read out the entire chip at one time. The disadvantage is that those little circuits will introduce heat into the system and hence create dark noise, which I will also show you later on. But the important thing here is actually to see that you have this little color biomatrix in front of your pixel. So this is one pixel here. So you have red, 2 green, and a blue, and then you can see this continues all the way down, and then you get a color image. This is the CCD, the what you call it, the star camera, the Astro Camera that I have. It's not a very big chip, and it's a color cam, so it has the same design as this here. I have an image of it here. You can see the main camera here, the guide camera here, some cables, and then you can see the filter wheel here. I'm going to go into what basically most of these things means. There's a power supply. You probably know what that means. But anyway, this is a big wafer, so you can see you have multiple different size CCDs put onto this round wafer here. This is so you can design the observations that you do. I seem to remember, but I'm not sure about it, that this is the same kind of design wafer that were used on SDSS, the Sloan Digital Sky Survey. Alright. Here you see the advanced camera for surveys that is going to be, that has been already placed on the Hubble Space Telescope in the clean room. As you can see, this is a big chunk of sensor. So compared with my little camera here, this is a huge CCD sensor. And you can pretty much imagine why the Hubble Space Telescope would be the size of a bus. Just going to get something to drink. Alright, so this is sort of introduction to some of the, you can also see it here, ACS. Advanced Camera for Surveys. This is just a basic introduction to the different CCDs that we can use in astronomy, from the very smallest to the extremely large. This is the CCD controller for the alphas. You can actually see the Cryotank here, and the CCD would be in here somewhere around. And the idea about this Cryotank is that on most consumer CCDs, even for astro use, particularly for astro use, we have 1 or 2 Peltier elements, you know, the funny thing that can transfer heat from one side to the other. Sorry, can transfer heat from one side to the other, so you can turn it one side and then you can make things boil, or you can turn it the other way around and make things freeze. But then you put 2 Peltier elements in a series, and then perhaps you use either just pure convection, convection, which means that, for example, my camera has I think it's a single Peltier element, and then it simply transfer that heat it cools the CCD down with, transfer that heat to the metal around it, and then wind or whatever it is, radiation will carry that energy away. You can also put a little fan inside it. You can actually see a fan right here. This is for the controller, but there is a fan there. And in the same way with a consumer Astro CCD, you could put a little fan to transfer more heat out. Modern Astro CCDs also have the ability to control the temperature, so instead of just cooling all the way down, you can actually say, well, I want -20 below ambient or something like that. No, not -20, below. It's -20. But in professional cameras, you actually use liquid nitrogen to cool the CCD down. This means that in consumer CCDs, the Starlight Express, SBIC, whatever you can get your hands on, there will be dark noise in there. On these chips, actually not on these chips, but also on these chips, but cooled down using this kind of material, you will basically get no dark current. I'm going to also get into what dark current actually is. Alright? So the filter wheel. This is a consumer filter wheel from, I think it's Starlight Express. It's actually an electronic version, so you can put, I think it's, 1, 2, 3, 4, 5, 6, 7, 8, 9 different filters in here. Yeah, it just says 9 here, damn it. And then you can say, well, I want to use filter, for example, you could put red, green, blue, hydrogen alpha, oxygen 3, silicium 2, I think sulfur 2, sorry. Then you could put BVR filters here if you want that. So if you want to use the V filter, which is here, then you just say, well, I want to use filter wheel 8, and then the filter wheel will automatically turn the filter wheel to get the correct filter. This is the filter wheel for the Hubble Space Telescope. It's a lot larger, and you have many more different kind of filters in here. This is all some of all the filters that you can use. Basically, what this F140 means, it means that you have this is a filter. It's at 1400 angstrom, and it's a wide field filter. This is for example a narrow filter, an N, and so on and so forth. These are the basic kind of filters that you can use for amateur astronomy. You have a luminance filter here, which is basically a filter that filters out sky glow and things like that, but then let every else kind of light go through. And then you have the classical red, green, and blue filters. I'm going to get into what these filters are for, but just remember that you can use independent red, green, and blue filters. So to some examples. Let's go on to that. Here you see an image of yours truly in colors. I will admit it, not really good colors, but nevertheless colors. But what you might be surprised to know is, but hopefully not that big a surprise now, because I've shown you how a CCD and a CMOS actually sees colors with the pixels. What your camera actually sees is this. Black and white. So you might think, alright, so my camera sees black and white. How then I get color? Well, you might be able to see, I'm not sure. You might be able to see some kind of grainy structure somewhere around here, some places. But nevertheless, I'm going to show you right here on my eye. You can see those patches here of black and not black and so on and so forth. This is due to the Bayer matrix. So this is what your CCD, this is what your CMOS in your iPhone, in your BlackBerry, whatever you use, this is what it actually sees. Then sorry, then some kind of electronics with a mathematical description on how to interpret the biomatrix will actually derive. Let's go a bit back to the part where we had the biomatrix here. So this pixel here will see only red. These two pixels here will see only green, and this pixel here will see only blue. And then of course the same goes for all the pixels around it. So let's say, well, the biomatrix and the mathematical formula used for the biomatrix then uses these adjacent colors to figure out how much green and how much blue goes into this pixel here. And also in this pixel here, figure out how much, also how much red, but how much blue, how much red, and how much green actually goes into here. And it uses the mathematical formula again to figure out how much green, how much red, and how much blue goes into this pixel here. And so on it goes all the way through. But all these kind of detectors, both CCDs and CMOS, inherently only sees black and white, or gray nuances, if you will, just like the rods in our, the staves in our eyes. That's it. Then we can superimpose this biomatrix on it, or we can put a color filter in front. And that is what these filters here are for. So instead of using this biomatrix, I can simply say, well, first I take, let's say, 10 minutes of exposure with a red filter. So my CCD in that moment will only see red in all the pixels. Then I go on to the green filter, again take 10 minutes of the same object in green, so all my pixels will only see green. And finally I do the same thing with the blue. Now you can imagine, why don't we use that? Because I will say that this is the best method, because no matter how perfect or how well this bias system actually works, and I must say, if you look at CCDs, at DSLR pictures, it works pretty well. Of course, this is a well-lit situation where you have a lot of pixels, but nevertheless, it works pretty well. But you are interpolating color information on a given pixel without knowing how much color you actually have there. So in some sense you are guessing what color should be there. It's a mathematical description, so of course in essence there's no guessing, you're simply calculating it, but it is interpolation of the correct color without really knowing what the color should be in that pixel. When you use filters like this, you don't have that disadvantage, because all your pixels in your camera or in your CCD will see, or CMOS will see, the same color no matter what goes on. If the color is there, the filter will, the CCD will receive it. Alright, so let's go on to, this is the example that we have. So, yeah. This is an image taken by me. It's a composition of 300-second exposures and 900-second exposures, I think it is. This is of the cluster Abell 2218. I was actually wanting to get an image of these arcs that you can see here. By the way, this is the Hubble equivalent. And the reason why I show this is that you can see, well, we have the stars here. You can see all the stars. They're there, and so on. Let's for a second imagine that NASA was faking all of this. So this would be a fake image. I can in no way imagine why NASA would try to fake something. And you can see that this is the same cluster, right? You have the bright central galaxy here, then you have a piece of galaxies out here, and then you can see all the galaxies that you can see on this image line up with the galaxies that you can see on this image, even though we have a lot of noise in here. Right? You can also see those down here, right? Okay. Why on earth would NASA go ahead and fake these things, right? When every amateur astronomy in the world could just point their telescope at Abell 2218 and then let the photons rip in, all of them, right? As you can see I've done here, I will admit that I haven't done a pretty good job because it's hard to actually get something out of this cluster in the conditions that I have with a lit sky and bad seeing. But there are other amateur astronomers that I know who has actually got a pretty good job in trying to get photons from this cluster, where you can almost spot some of the brightest arcs here, but it's there. And just to be clear, I'm pretty sure that this is not an arc, because you can see this is blue and this is blue, so this is those two galaxies here. But you can see that these are the, and if I sort of zoom a little bit out, you can pretty much see that this is the same object, right? If you can't, then you need glasses, because it is the same object. You can't, unfortunately, cannot see these three stars here. They would be somewhere around here, but you can see that this star is here and so on. So this is the same object, right? So if I were NASA and I were going to fake something like this, I would pick something that amateur astronomers can't observe. For example, the very deep field or the extremely deep field, that's pretty much inaccessible for any kind of ground-based telescope. It's actually the reason why they pointed the Hubble Space Telescope in that direction, is because no ground telescope has observed anything there. But a cluster like this and big bright galaxies, which I'm going to present later on, that any amateur astronomer can observe and check for themselves, why on earth would NASA go and fake something like that? That wouldn't make sense. They would be called out immediately. People would go out and say, well, no, this is not true, right? So I will tell you why we have the Hubble Space Telescope. And the main reason, the main answer is because of seeing. On Earth, we have to look through the atmosphere. And for someone like me who lives in Denmark, I think it's latitude 54 degrees or something like that. There's pretty much atmosphere to look through, and the seeing is not that good actually. And besides, we have a lot of clouds here, so there's not much time to observe in any case. But we have seeing, so the good seeing here would be probably 1 arc second. It's more likely to be 2 arc seconds in seeing. So just basic astronomy lingo introduction. When we look at a star under perfect conditions with the perfect telescope, we would see a point, because that star is so extremely far away that we cannot resolve it in any structure. We have a couple of stars. I think Betelgeuse is one of the stars that we can actually resolve as more than just a dot. But basically any star that we can see, which I would like to remind you is more or less in our own galaxy, is only a dot on the sky. But when we look in a telescope which is not perfect, that dot begins to get a shape. It begins to get size. Add atmosphere to that, where we have turbulence, winds moving around, it would, because the star would move around in an erratic fashion, it would blur the image out. And if you collect enough photons with this blurring, it will create in more or less pretty much quick time somewhat perfect circle. But it will bloat the star and ruin the resolution, the fine resolution we can get on our telescopes. Since the Hubble Space Telescope is outside our atmosphere, it doesn't have that problem. It doesn't have atmosphere to look through. And that is why the only obstruction from perfect resolution on the Hubble Space Telescope is the theoretical resolution of the telescope itself and the resolution of the sensor. And from the top of my head, I think to recall that it is somewhere around 0.05 arc seconds, something like that. So it's heck of a lot better than 2 arc seconds. It's below a half arc second. So that is why the Hubble Space Telescope has such a tremendous resolution compared with ground-based telescopes. But there are some ground-based telescopes that by pointing a powerful laser at the sky, and then creating what is called a fake guide star, the telescope observes, or part of the telescope observed that fake guide star, which will move around according to the turbulence in the atmosphere, the seeing, as we call it in astro lingo. And then a computer will try to use active optics and adaptive optics to alleviate this movement of the stars, hence giving much finer resolution. But I have heard of 1 or 2 telescopes, professional telescopes that is. These corrections are going on the primary mirror, basically. But what they have done is also to apply this on the secondary mirror, hence giving resolutions that can actually compete with the Hubble Space Telescope. But as far as I remember, it's a pretty hard maneuver to do because you actually have to use some kind of magnetic construction to keep the secondary mirror up so that you can correct on it. But that's the basic thing. But the reason why we have used the Hubble Space Telescope, and because it's so popular, is because it gives us very fine, high resolution pictures, and we can observe for a longer time in a stretch. On Earth, we are confined to the night time, even though we place our telescopes near the equator. Alright, so let's move on. This is an image I have taken also with iTelescope. As you can see, this is a much better resolution. You can see the stars better and all those sort of things. This is actually, this is just a larger CCD with a bigger telescope. Now I have removed some artifacts because this is what it called a non-anti-Blooming Gate CCD. This basically means that you can view the pixels on a CCD as little buckets that can collect photons. And as you can probably imagine, if we collect enough photons, we will get an overflow and we will spill on to the adjacent pixels. And this is exactly what happens on a normal CCD. So you will see these long stretches down, which is because the pixels has actually overflown downwards here. This happens on what is called a non-anti-Blooming Gate CCD. On a Blooming Gate CCD or anti-blooming CCD, you will have some electronics to pick up those extra electrons that gets filled up because you have reached the maximum well depth of your pixel. So, but I have removed those from this picture. But otherwise than that, the only thing I have done with it is to bias subtract it, dark subtract it, and divide by flats, and then combine it in red, green, and blue. I have taken both red, green, and blue wide filters, and then hydrogen alpha, oxygen 3, and sulfur 2 narrowband filters. So this is a combination of all those things. But this is an image I have taken myself. The same goes on here. I think it's M81. You can see there are some things going on up here. I think it's because of the moon. But other than that, a nice picture where you can see the galaxy here. This is taken with my own telescope. This is the, I think it's called M33, the Triang Galaxy, I think it is. I'm not sure. I would like for you to notice two very clear things. One noticeable things, that you have some kind of big nebula thing here, and then you also have a very big nebula thing here. This is taken with my telescope, as you can see here, on between the 22nd and the 23rd October, between 2333 and 0.25. I'm not sure what year. I think it's 2015, perhaps 14. I'm not sure. The camera, my Starlight Express MG7C, on my 8-inch Newton with guiding on through this refractor on my EQ6 Pro. It is composed of 14 300-second exposures in RGB because it's a color CCD. I've bias subtracted it. I've stacked it with what is called an SD mask, edited with stretch, curves, and so on and so forth. And a DDP uses settings like this, and it's taken in Ringsted here in Denmark. This is an image by me. So let's move on. This is the same galaxy seen by ESA. I think it's the Very Large Telescope. It's not the Hubble. You can see this here is what you see here. And I'm pretty sure that what you see here is this up here. So this is the same freaking galaxy. This is not fake. This is certainly not fake because I've taken it myself. You can also see, you can actually see very big stars here. I can resolve stars myself on this image. As you can see here, they have a lot of more detail. Of course they have. It's a bigger telescope, more exposure time, better conditions, better seeing, better all of these things. But this and this is the freaking same thing. Why on earth would they go and fake something like this? It would be utter nonsense to do that. Let's move on. I think I'm not sure this is called the Pinwheel Galaxy. I think it's called Measure 51. I'm not sure. Notice that we have a merger galaxy here. It has a very characteristic structure. You can see it. It is also taken by me. I have not added meter information here, but it is taken by me. It's taken by my CCD. You can also see that it's roughly the same shape. Sorry, not shape, size. CCD. This is an image taken by the Hubble Space Telescope. Besides of the resolution and the details, it's pretty much the same thing, right? No? Yes? I would say so. Of course they have a lot of more details here. Really a lot of more details. They can actually resolve individual stars in this image here. And they have used a lot of more filters. Remember, I have only red, green, and blue in the Bayer matrix. They have probably used a lot of wealth of both wide band and narrow band filters. But these two galaxies are the same thing, right? You can see it. Also this kink here, right? You have it here. Why on earth would NASA fake something like this when everybody with a telescope can and a CCD can take an image like this and just call them out and say, hey, this is not how it looks. But it is. Why would you fake extra details? It doesn't make any kind of sense, right? Who would you convince of anything by faking details on a galaxy that anyone with a CCD can observe through a telescope? Right? Oh, well, yeah, no. You can actually see this part here. This is the part here. I have actually that width on my image in order to make myself proud, a little bit proud of myself. This is actually a pretty good image. And as you can also see, the seeing and the focus was pretty good. But you can also see the bands here, right? The bands in the arms, spiral arms here. I have those as well. So why would NASA fix something like this? That would be totally stupid, extremely stupid. So let's move on. This is the Pinwheel Galaxy, I think. Pretty sure. I think it's M101, I think it is, right? You can also see a pretty convincing, a very apparent structure here. You can see something down here, and then it has this characteristic pinwheel structure, right? Again, an image taken by me, by my M7C camera, color camera. The focus, I think, is not pretty good, and this was also before I learned to use flat field subtraction division, so there might be some blemishes and those sort of things from my telescope. But all in all, this is a galaxy. This is pretty much apparent. This is the same galaxy through the Hubble Space Telescope. Again, notice this part here looks pretty much like this part here, right? The same shape, look like a J, for example. Sorry. Yeah, pretty much a J. Down here you have, what should we call it, an ice cream? Yeah, the same thing, right? I even have this weak part out here on my image. So these two galaxies, let's say it like this, are the same. They are definitely the same. Again, same story. 3 stars out here. Now we can actually see the advantage of the Hubble Space Telescope, right? These 3 stars out here is almost, if I put my head really close, I can see that this is 3 stars, but they are almost the same structure, right? They are not well resolved. The theoretical resolution of my telescope would be able to resolve this. Hubble Space Telescope, 3 stars. You can easily see that this is 3 stars. Right? You can see the star here. I have it here. 3 stars. Star here. Star here. Yeah, you have this triangle shape here, right? You can see that they have tilted the image a little bit. That's because I haven't actually conformed my image to the standard, which is north up and east to the west, to the left. But of course they have done here because this is NASA, right? This is the same goddamn image of the same galaxy. I wonder if let's see, star here. Yeah, I think this is the one, perhaps. Yeah, this. Sorry. This might be the little galaxy I have here, but in any case, well, this is the same galaxy. Let's just agree on that. Again, and this is the Boats galaxy, which is also taken by me. Alright, so let's look a bit at the CCD calibration, because one of the things that I also heard from flat earthers is that we manipulate the data. This is faked, it is CGI, it is composites, what have you. So what is an composite? Let's take one of my images, for example. Let's take the first images that we saw. You can see this is a full frame image of the whole galaxy. This is sort of parts of the galaxy. What could I do in order to get a better view of the galaxy? Well, perhaps I could take the same image out here, the same image out here, the same image out here, and the same image out here. If I had a black and white CCD, I could also take it in red filter, green filter, blue filter, narrowband filters, so on and so forth. And I would then have 4 separate images that I combine into a mosaic image of this galaxy, hence getting all of the galaxy on my CCD, on my image. And also I would combine the color information from red, green and blue and so on into a composite image. That is what is meant in astronomy by a composite image. Let's move on. So what are the problems with CCDs? Well, CCDs are given an offset from the electronics, by the electronics or in the electronics. That's because we want to make sure that the base voltage, or what you want to call it, on this CCD is the same. So they're given an offset sort of to lift the counters up roughly at the same place. CCDs also have inherent noise when we capture photons. So if you take, and that is why it's called dark frames or dark noise. If you take a CCD, you completely isolate it from light, put it in a box, and then make it expose, you would see something on the CCD. It would not be perfectly black, and that's because that you actually have heat in the CCD that will make that will release electrons into the CCD, which will act as a counted. It will count as as exposed. Sorry about that. And that is the inherent noise when capturing photon. That's dark noise. Also, CCDs are not perfect receivers. They might not be perfect illuminated, and they might not receive the light perfectly, all the pixels. And also, they are, like I said, they're not perfectly illuminated. That might be also blemishes. There might be imperfections in the optics. There might be blemishes, what we call donuts on the line of sight, and all that. And that is why we take that. That's what called flat framing. I can sort of introduce what the things are called right now. All right. So first of all, we remove the offset, and that is by making a bias frame. Actually, we make a lot of bias frame and then combine them, but a bias frame. So a bias frame is that you cover up your CCD, and then you take a 0-second exposure, or as close as you can get it to that. So you just get the offset of the electronics. Then we remove and as I said, the bias frame is pretty quick, so you can take a lot of them because it's a 0-second exposure. The dark noise, however, has to be the same exposure. The dark frame has to be the same exposure as your light frame. So if you take 600 seconds exposures of an object, you would need dark frames of 600 seconds, preferably 10 dark frames or more to be combined. That's a detail, but just to put it out there. And again, you cover up the CCD, and then you let you expose the CCD, and then you get the dark noise. You combine the dark frames that you get into a master frame, and then you can subtract the bias frame from that, and then you have something that you can subtract the bias from your light frames, and you subtract the dark from your light frames. Finally, you make the field flat or evenly illuminated by taking as an exposure where you don't saturate your CCD on an evenly illuminated surface. Now, a popular thing to do is to take what's called twilight flats, which means that you can point your telescope at a given position on the sky, at twilight, and then you can use that to make flats. There's no preferred or demanded exposure time here. The only thing to notice is that you don't saturate your CCD, because then you can't use the flat frames. And also it's very important that that what the CCD see is evenly illuminated from the outside. You cannot. The idea is to alleviate if there's an unevenly illuminated path of the light in your system and also in the CCD, but the outside source should be evenly illuminated. Another thing you can do is to make what is called a flat lamp. You simply take, for example, the white white background in a laptop screen, and then you can use that to get an evenly illuminated surface, and then you put that onto your telescope to take the flat frame. What is best? I think it's a matter of opinion. Of course, I would argue that the twilight flat is the one that takes the least amount of work to actually get done, because you can take it before you observe and you can also take it after you observe. Alright, so let's show. Here's a bias frame from one of the iTelescope CCDs. I think it's Telescope 11. You can see there's a streak here, and this is one of the things that you can also alleviate with your with this bias frame, but nevertheless there is an offset here that you subtract. This is a dark frame. You can pretty much see why it's called a dark frame. All these little dots here is dark noise. So this is when an electron gets knocked out and registered because of heat signatures or anything of the sorts. In a frame like this, you can also sometimes see cosmic rays as sort of a long streak across the CCD, but this is generally dark noise. Finally, you can see the flat frame. This is for a V filter, and you can see that out here you actually have you can see that the CCD, the path of the light is not evenly illuminated. It's very bright in here, and then it gets gradually less bright, darkens out here, until you reach here where there's sort of a barrel shape. And this is what the division with the flat frame ensures. Also particularly important if you're doing photometry. You need to make sure that the counts that you get, because you're essentially counting electrons from a star to convert that into a magnitude or a flux, you want to make sure that what you are counting is actually what you're counting. Alright. Then finally this little image here that I took again at the Nordic Optical Telescope. And one interesting thing is that I think this is the North Star somewhere around here. And as you can see, all the stars move around it. Actually, this way around, but anyway. I would say, this is just an assertion, if you will, on an assumption from my case. But I would argue, with my scientific background, for this here to happen, because you can almost see that the North Star is almost, I think the horizon is out here somewhere. You can almost see that in order to get the North Star this far down, compared to, for example, where I live, where the North Star is pretty high on the sky, on a flat Earth with less than on a flat Earth, sorry, you would have to have the sky pretty close to your head. I would argue that if you go into a big church, for example, with, let's say, 15 meters to the ceiling, something like that, you stand underneath something very apparent, look at it, and then you move, let's say, 5-10 meters to one direction, and you would also still look pretty much upwards, even though you have moved pretty far, if there's high enough to the ceiling. Now remember, most flat earthers that I have heard about or talked with say that the distance to the sun and the moon should be roughly 3,000 kilometers, I think it is, or it's 3,000 miles, I cannot remember. And so it is reasonable to assume that the distance to the stars is at least that much. I would argue that if the Earth were flat, and I would see this, the Nordic Optical Telescope, you can look it up, it's roughly somewhere around the coast of northern Africa, somewhere around there. It's called La Palma, the island. It's part of the Canary Island. I would argue pretty much that the sky would have to be much closer to us than 3,000 miles or 3,000 kilometers in order for this to happen. Actually, perhaps under maybe under 100 kilometers, something like that. The edge of the atmosphere, something like that, yeah. So I would argue that this image in itself is somewhat a proof that the Earth cannot be flat. But, of course, a more direct evidence for this is to look at, for example, how the shift goes when you look at the north celestial pole and then go to the south celestial pole. They both move around the same fixed point. Of course, the north celestial pole moves around the north celestial pole, and the northern hemisphere, of course, moves around the north celestial pole counterclockwise, and the southern hemisphere moves clockwise around the south celestial pole. But I simply cannot imagine that this, or explain with physical knowledge how what we see would be possible on flat Earth. I simply cannot. So with that, I would say bye bye and thank you for watching this video. I will be strongly back later with something new. Bye bye.